LPTMS session, and we have now Dmitry Petrov from LPTMS is going to give a talk on beyond mean field effects in quantum gases.
Give me a sign, like 5 minutes in advance. Can
yes.
Or maybe 10.
10. Okay.
Can I start?
That's true.
Yeah, I just wanted to thank Raul, but he disappeared. So he actually constrained me a lot, saying that my talk should be understandable.
You speak louder.
Ah, all right. And see, you constrain me also. All right. So I'm not gonna speak about preliminary results that I obtained last week. So I have to apologize that it's gonna be a talk about something that I did a few years ago. But I think that given the context of this meeting, this would probably fine if you just hear the flavor of what I'm doing in the last years. And yeah, so I'm going to talk about beyond mean field in quantum gases, and more precisely in quantum droplets business that was cut because it didn't fit into the poster, you know, the second part. So I start with this iconic picture of BEC that came from Gila from '95. And you see what is characteristic about Gila is that they call it a new phase of matter. Right. So since already now more than 27 years, we believe that, okay, this system is a very dilute gas. Right, so typical von der Waals range, and the range of the interaction is a few nanometers, and the mean interparticle separation is 2 orders of magnitude larger. So, and basically this system exists in two. Okay, so the energy density, interaction energy density, is basically the number of pairs in the gas multiplied by the coupling constant. And this coupling constant is basically what you can change. So it can be positive or negative. If it's positive, then it's a gas, and it requires trapping. So energy density goes like this with density n squared. And if it's if you tune your coupling constant or scattering length to negative values, it collapses. It just wants to go to reach this high density regime by doing 3-body recombination and trying to reach the metallic, the ground state. Now, recently there have been experiments on yet another new state of matter, which is called liquid, a dilute liquid actually, where gas in this. Well, I give 2 examples. This is a dysprosium highly magnetic atoms, BEC of dysprosium, which by tuning the interaction, it actually has a tendency to collapse, but the collapse is stopped for some reason, and you observe droplets like this. See, so it's not collapse and it's not a gas, it's a self-trapped state. And similar pictures you see also from experiment on 2-component potassium gas, which is not magnetic, weakly magnetic. We have droplets there. So this experiments and also theory has stimulated lots of progress, and now it turns out that this phenomenon is due to beyond mean field effect, due to the so-called Lhy correction. And now we basically, in the last 5 years, we learned a lot about this perturbative correction for this reason that it actually can be visible in the experiment. So this liquid, is it really a liquid? A liquid requires that your density, energy density, has this characteristic concave shape somewhere that connects the vacuum and the matter. So this is, by the way, the first order transition between vacuum and matter. It's a droplet. So in order to organize this in the ultra-cold gas, basically we have to guess that there is a beyond mean field term there, which scales with a higher power of density, and it gives you a repulsive slope there at high density. So people discussed that relatively long time ago, and the most natural choice is like to introduce a three-body repulsion there. That was proposed by Bulgak 20 years ago. And this is actually a natural kind of way of, expansion of the energy density in integer powers of density is a natural thing, particularly from the nuclear guys, and who is, the guy comes from there. I also work on that in other setup, but eventually I also work on this Li-Huan-Yang type of stabilization mechanism that gives you some kind of 2.5 body repulsion there, because the power is 5.5, and this is this beyond mean field quantum mechanical stabilization mechanism there. So before I get into this, and it's actually quite interesting that this new state of matter comes also with new terminology that was not usual in the ultra-cold gas. And for instance, now we know that liquid is not, like, semantically, it's not equal to fluid. Although in, I don't know, in my native language, these two words are the same. We know about saturation density is the density of the fluid, that exists in equilibrium with vacuum. The particle emission threshold is minus chemical potential. The chemical potential is negative, so minus chemical potential is a positive quantity. If you try to excite your liquid or droplet with frequency higher than this, you kick out particles out of it. Surface tension, surface modes, etc. So what is this quantum stabilization mechanism? So the simplest explanation that I find is that, consider a classical problem. Well, consider a particle in the, let's say, parabolic potential. So classically, its ground state is just it is in the bottom of the potential, and the BEC analog of this, which is basically many of such particles, right, is just, I see it as a kind of a string, classical vacuum, and the BEC analog is the Gross-Pitaevsky equation, right? Now, when we switch on quantum mechanics, we know that the energy, we have h bar omega over 2 energy shift, 0-point energy, and we have 0-point motion. And the BEC analog is like mean field Gross-Pitaevsky plus Gaussian fluctuations, which is the Lhy correction. Okay, and I envision it as like a string, which when you make a picture of it, it is in the ground state, but every time you make a picture, it is bent like this, and then you make many pictures, and it's all smeared out, and it looks like this, in my mind. Okay, so let me do this experiment that I actually invert the parabola. So the classical problem is unstable. So the particle will just go search for the ground state elsewhere. But quantum mechanically, it does not help. Actually, the switching on quantum mechanics does not help, because this it's also unstable, and it's a collapse. The BEC analog of this is a collapse. Can there be a classically unstable system that can be stabilized as we switch on quantum mechanics? And probably the simplest thing is to consider, okay, so the system should be minimally more non-trivial. So in this case, I consider a two-dimensional particle in a relatively exotic potential. So this potential has a valley, the bottom of which, well, in the direction x, right, it's unstable. So classical particle would just go down the valley and the classical solution does not exist or exist at x equals infinity. But I imagine also that the valley has this mountains around it, and the frequency in the bottom, it actually increases as I increase x, so that my h bar omega over 2 has an x dependence, and it goes up faster than the bottom of this thing goes down. And when I switch on quantum mechanics there, this particle is stabilized because of the quantum effects. So it is squeezed well, you see what I mean. So, and this is the BEC analog of this is my quantum droplets, more or less. And now I will try to discuss it more in detail. So what is LHY mechanism? I don't know, probably seen this formula. This is the next, okay, so this is the energy of a spinless Bose-Einstein condensate in the weakly interacting regime. So the first term is the mean field term, as I said. It's just a scattering coupling constant proportional to the scattering length times the number of pairs, right? And the next term goes with this gaseous parameter in an relatively exotic manner, because it's not an expansion in integer powers, but it's non-analytic, which made excitement in the 50 years ago. So it is still exciting. It comes from the fact that if you have infrared divergence, if you do the usual perturbation theory, and this infrared divergence is cured by the Bogoliubov theory. Is cured by the Bogoliubov theory. This divergence is cured by the Bogoliubov theory. If you do a usual expansion in powers of interaction, you will end up pretty soon with a divergence, infrared divergence. And Bogoliubov kind of solved this problem. Okay, so people are also excited about this correction because it's universal. It depends only on the scattering length. So it does not take into account any, structure of the potential. It just takes only the scattering length into account. And it's quantum because it's basically the sum of the 0-point motion of my h bar omega over 2 of all bosonic modes, Bogoliubov modes. Okay, and therefore there were quite a bit of activity in our field on observing this beyond mean field effects. And this is one example. This is the picture from ENS, from the group of Christophe Salomon, where they measured the equation of state. So it's a pressure is a function of reduced chemical potential. So the point is that this would be your mean field, the red line, and this is what they see. And this is mean field plus LHY. So
here they check 5-half experimentally, is what you say?
They check even the coefficient. I mean, you see, this is the prediction given by this formula. And this is just a pure mean field. So, okay, so the fundamental issue has been checked, kind of. Of course, when you know what you're looking for, you tend to find this, right? So, okay, so the question for me is that, this thing, if you, as I explained, so you invert the parabola. So in this case, I change the sign of the scattering length. The problem is that when at the point where scattering length is 0, the beyond mean field correction is also 0. It actually goes faster to 0 than, and it makes a, okay, so here there is no, it's not interesting to measure it. But there you get into a strongly interacting regime and you have all other problems there that would come in. So, okay, whether we can do this, whether we can control mean field and beyond mean field independently. The answer is yes, you can do this if you go to the Bose-Bose mixture, at least. So your system would be minimally non-trivial. So it's a Bose-Bose mixture. Instead of Gn squared over 2, you have a quadratic form for the energy density, which is depends on now 2 densities and 3 coupling constants, right? And this quadratic form, if you plot it as a function of densities, is just what is it? Paraboloid, and the paraboloid can be elliptic when all interspecies coupling constants are positive, and the interspecies one is between minus geometrical average and plus geometrical average. So you have this thing, and everything is stable and nice, and you have a mixture. The mechanical instabilities happen when you are too strongly interacting between the, when the interspecies interaction is too strongly attractive or repulsive. So in this case, you have a collapse. In this case, you have the your paraboloid become hyperbolic, and the collapse happens, along this valley. Kind of the system tends to collapse, keeping the ratio between the densities. And there is another phase separation that I started, but I'm not going to talk about this today. So now, what do we do when we see a quadratic form? We tend to diagonalize it, right? So I will be interested in the small vicinities of this, in the small vicinity of the collapse point, and I introduce delta G, which is given by this form. Okay, so it turns out that when you diagonalize this thing, you will have a stiff direction like mountains and a valley, so like this. And this n minus and n plus are new densities. Basically, it's if you want, this is the total density, and this is the spin for symmetric situations. This would be relevant. Okay, so now you have essentially, you instead of a mixture, you end up with the system. If you just integrate out this spin degree of freedom, then you end up with essentially a scalar gas again. Right? And then when you add the LHY, I'm going a little bit too fast, but if you add the LHY correction there, the point is that you will have your 5/2 there, because it depends on the velocity of sound of the spin mode in this direction, and it gives you n to the 5/2. And now you have a competition. I want to have a competition between this delta G, which is supposed to be small. That's what I call mean field interaction, because this one is kind of frozen, the spin component. And the LHY correction, which is then of the same order of magnitude. So I have a competition between two equally strong corrections.
So why have you written plus and minus? So you have written
yes.
plus or minus.
Yeah, sorry. Okay. Because I recycled this slide. So plus stands for phase separation. Just a second. No. Plus is for collapse and minus is for phase separation, I think. But okay, just keep on the plus there. When delta G is negative, you collapse, and then this thing goes kind of down like this. Let me skip that. I'm sorry, but I will return if you have questions. But okay, so this is the okay. So this is how it is. The formula for the LHY correction for a mixture, the general thing. And what I wanted to say is that it actually, the LHY correction is the sum of the 5th powers of the velocities of sound. So you have a mixture, you have two Bogoliubov modes, which are just normal Bogoliubov modes, which are given by some parameterized by speed of sound, C plus and C minus. Close to the collapse line, one of them becomes very soft. And if you go down there, it will develop imaginary frequencies, and this corresponds to this collapse tendency to collapse. But the spin mode is stiff, and this is the point is that this spin mode gives you a finite LHY correction there, which is scales as which is repulsive and scales as n to the 5/2.
I had understood that the eigenmode of the quadratic form was becoming softer, not that
yeah, but
the part that comes into.
Yeah, so you can do it by diagonalizing the quadratic form in densities, or you can also do it by using the Bogoliubov modes, and you will see that at the same time as the density mode becomes unstable, the velocity of sound which I call C minus, will also go through 0 and become imaginary, which is compressibility. Speed of sound is the compressibility is the same thing, more or less. But okay, they are related. They happen at the same time. They are related, yes. But here I want to say that this mode does not contribute to the Lhy correction, because in the scalar gas, when you make your speed of sound to 0, the formula is the same, except that there is only a single speed of sound. The speed of sound is 0. It does not contribute in the spinless case. But in the mixture, what contributes is the other mode. This is unstable, but the other mode contributes. So you have, let's see what I have on the next slide. Okay, well, I don't want to speak about that. So this is what you see if you add the Lhy correction there. This is this picture, but add Lhy correction there. And then you will see a minimum there. Well, actually, it's a concave shape. So if I plot it only the bottom, I have my curve like this. So a nice thing about it is that you can control your saturation density by changing delta G. When delta G is small, the saturation density is small. And it can be dilute. So it's a dilute liquid. It's actually amazing because there is usually the van der Waals liquid, its density, its mean interparticle separation corresponds to the van der Waals length. But here it's not. It has nothing to do. It's just it can be much larger and it can be controlled. 10 minutes. Fantastic. Okay. Okay, so this was for the thermodynamic limit. But if you have a finite number of particles, you can actually, the theory is very well controlled. There is a small parameter. You can write down the Gross-Pitevsky equation, and under proper scaling, it looks like usual nonlinear Schrödinger equation with cubic attractive and repulsive quartic nonlinearities. And you can actually see if you have many particles, you have a droplet with a bulk flat density profile. And then when you decrease the number of particles, it shrinks. So these are actually the wave functions of the droplet, right? So it's for large number of particles and then it shrinks. And then eventually at the critical particle number, it is no longer bound. So the state becomes unbound. And this is basically, and then you can study excitations of this droplet. When you have big droplets, so these are basically surface modes, and bulk modes, which are actually more stiff. So in this, here I plot the energies of the frequencies of the modes as a function of number of particles in a rather exotic manner, but does not matter. So large number is here, small number is there. So you have the surface modes that go, when you decrease the droplet, they go out in they cross the particle emission threshold, and that means that you cannot excite them. You try to excite them and you emit particles there. And the breathing mode actually does something like this. So it goes like this, it goes to the continuum and then comes back, and it's this mode, the zero frequency of this mode is related to this breakdown of the binding. Okay. Yeah, so interesting point is that in contrast to other systems, you have a region of parameters where you have a droplet without any internal modes. So if you have it, you are sure that there are no excitation there. It's a self-evaporating thing. So it's a macroscopic object at zero temperature. Okay, what I just re-put this slide just to show that these are these droplets actually that were observed in IPhT in the group of Laetitia Taruel. Maybe I have a few minutes to show you what's the relation of this mixture to the dipolar case. The dipolar case is not a mixture; it's a scalar gas, but it has a exotic interaction. So it is anisotropic and long range, and the result of this is that if in the mixture you have two modes, one is soft and one is stiff. The soft mode is kind of unstable. The stiff mode gives you the Lhy correction. Here you have a single Bogoliubov branch, but it's anisotropic. So the speed of sound of phonons in the direction along the dipoles is higher than the speed of sound in the perpendicular direction. And the collapse in the dysprosium case happens actually, it's anisotropic. So the gas has a tendency to form these needles like this. So it collapses in radial direction. So this direction is unstable, but it's stabilized by phonons that propagate in the other direction. And the Lhy correction is also, it's just an average, angular average of the speed of sound. It's also n to the 5/2. It actually works quite nicely, you know, if you do this Gross-Petaevsky equation, and it describes this droplets quite well. Okay, this was, you know, what I've told you is a few years old, and then my activity, further activity, is related to studies like extensions of this. So the point is that this BMF beyond mean field world is pretty rich, and you can see it from, for example, from this example that I showed you, you know, particle in the trap, but you change the geometry of the trap, keeping the ground state kind of, no, sorry, classical ground state the same. So I want to say that systems with the same mean field can have a very different beyond mean field life there. Yes, so I just tell you that we studied low dimensional droplets with Grigory Astrokharchik, who will be visiting in June, actually, for 3 or 4 weeks. We studied the Lhy correction and dimensional crossover in collaboration with people from Germany. With Thomas Bourdelle from Institut Optique, he's an experimentalist. He studied potassium with RF coupling, and we just had a paper on that, experimental and theoretical. And the PhD of my student, Alexander, was basically all devoted to three-body interaction systems. And I also, you know, I told you about the threshold for the collapse, but there is also another, you know, mechanical instability of phase separation. We studied the influence of beyond mean field effects there. And yeah, with this, I thank you for your attention.
Okay. Thank you. So do we have questions?
Thanks. So in the Gross-Petaevsky equation that you wrote with two nonlinear terms, does that include the, so that one, does that include already beyond mean field correction?
Yes, it's included in this term, quartic one.
So how does that work?
You mean why it is legitimate to include it, or how it came from this? Where is it? Yes. Okay, so mean field is n squared. In the Gross-Petaevsky equation, when you vary it with respect to psi star, it will leave you cubic term.
Yes.
Right? But if you have n to the 5/2, this is 1 the power of psi more, and this will give you
I see.
a repulsion.
So it comes from this Li Yang Huang results of
Yes.
5/2. Okay, I see.
This is how you pronounce it correctly.
Yes. So for the Gross-Petaevsky equation, we also have self-stabilized vortices and all of these kind of excitations, right? Do you
Self-stabilized vortex?
you have vortices, right?
Okay.
In the Gross-Pitevsky. Do you have these kind of things here? Because you mentioned regions where, I don't know, where things differ. You don't have bulk excitations. Or...
Yeah, so, okay, this picture that you see here is like very far, at very large number of particles. And this is what I was talking about. This is more like what we have in ultra-cold gases. They are somewhere here all the time because they don't have enough particles. The problem is that, okay, so there are two ways of either you add particles to go there, or you change delta G. You make delta G larger to go there. But then it increases the saturation density, and you're no longer in the good regime and well in the stable regime. So they are bound to be here. There are no vortices in this regime. It's too costly, too expensive. But there, of course, it's, you know, in the bulk, it's just the usual superfluid.
Okay, thank you.
Okay, other questions? Okay, I have a question. You, at the beginning, you mentioned this N-cube correction, this Efimov three-body term, and then you didn't mention it after that.
Yes.
Why?
Yeah, because you gave me a sign of 10 minutes and I was panicking.
You asked me to give you a sign of 10 minutes.
Wow. Let me just, since you asked, right? I will. Okay, so the Lhy correction depends on many things, on the density of states, on the spectrum of Bogoliubov excitations, on dimensionality, you know. So we've considered, so it turns out that as soon as you, okay. So what I told you is this picture, right? So you have two sound modes and the Lhy correction is n to the 5/2. But let's assume that you introduce the Rabi coupling between these spins. So you have potassium up, down, and you couple them. So introduce this term in the Hamiltonian. Right? So the excitation spectrum becomes like this. It gaps the spin mode, the coupling. It turns out that if you do the Lhy theory, the Bogoliubov theory, and calculate the Lhy correction in this case, instead of this non-analytic n to the 5/2, your Lhy thing will be renormalization of the two-body term and the three-body term. It has to be like this because, as I said, this factor comes from infrared divergence there in the, but here we don't have it because it's gapped. Therefore, we have three-body term. And this term actually has been measured last year in the, I wanted to show you, but I don't have time to explain what it is. But basically, the difference between this guy and that guy is the three-body term. So they've observed it.
Okay, thank you.